Okay, so today I'd like to show you that there are some applications to the math that you've been learning and the statistics that you've been learning in physics, and that you're not just learning it for the math's sake. So here we go with a couple, about three, I guess, physics distribution functions. So the first example is the Maxwell distribution for ideal gas speeds and energies. So you're probably familiar with the ideal gas law. PV is equal to nRT, where P, V, and T are the state variables, pressure, volume, and temperature, N is the number of moles, and R is the gas constant. So the idea is that we can relate the molecular model of an ideal gas to these macroscopic properties. So in other words, let's say that you have a collection of a mole, 6.022 times 10 to the 23rd, of an ideal gas. You have a mole of atoms of an ideal gas. You could watch those atoms bounce around and then describe the microscopic characteristics, such as the speed, the average speed of those molecules, say for example, and you could relate that to the macroscopic qualities. And you just do that through classical mechanics. You just treat them all as little elastic balls that bounce around off each other and undergo elastic collisions with each other and with the walls of the container, and you can apply Newton's laws to them, and you just do it in a statistical distribution. So this is a classical, purely classical description. So in order to do that, you just have to have certain assumptions that go on. First of all, you need to assume that you've got a lot of gas molecules, a few moles, okay? You can't just have 10. That's not going to work. You also have to assume that the average separation between the molecules is large compared to their dimensions. This is kind of one of the assumptions for a gas anyway. So if the molecule is only, say, a few tenths of a nanometer across, then it should be separated by several tens of nanometers apart on average. And they do obey Newton's laws of motion, but as a whole they move randomly, so it would be really difficult for a mole of gas atoms, for example, to predict the individual motion of one atom. You could do it, but you probably need a supercomputer. You can also assume that the molecules interact with each other and the walls only by short-range forces during elastic collisions. In other words, they don't feel a coulombic or a charge attraction to one another. They're not going to bond. They don't really strongly want to interact with one another. So you need pretty much inert gases that aren't going to chemically react with each other or the walls in order for this model to hold. And it helps a lot if you have a pure substance of identical molecules for this. Okay, if you do that, if you model it that way, then you're going to get a certain distribution of the molecular speeds, okay? So, for example, here is plotted on the vertical axis the number of molecules with an average speed of v, with speed v, versus the speed v on that axis, okay? This is called the Maxwell-Boltzmann speed distribution function, after the two gentlemen that came up with the statistics and the distribution function that describe this collection of molecules, Maxwell and Boltzmann. So here you can see that this is not a symmetric distribution function. In other words, if you folded it in half, it wouldn't lie on top of each other after you folded it about the middle. You have the most probable speed, okay, and that's at the peak of the curve. You have your average speed, which is to the right of the most probable speed, and then you have your root mean square speed, which is to the right of both the average and the most probable. And of course, we need these three speeds to describe this distribution function well, because it's not a symmetric distribution function. It has that long tail, okay? It's limited on the left-hand side because the lowest possible speed is 0. This is speed, not velocity, so it's the magnitude of the velocity vector. So the smallest that it can go is a 0 speed. And then, of course, to the right, it can go to a whole range of high speeds. That's why it's skewed right. So if you want to know what the function is to describe this distribution function, here it is. So here n sub v is the number of molecules with speed v. And then of course 4 pi, and then n, capital N here, is the total number of molecules in the collection. And then you have m over 2 pi kt to the 3/2 power. Here m is the mass of the gas molecule. K is Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin. T would be the temperature in Kelvin. And then you multiply that times v squared e to the minus mv squared over 2 kt where v is, of course, the speed. Now, this isn't a probability distribution function, okay? It's a number distribution function. It gives you the number of molecules with speed v. You could easily convert it, however, to a fraction just by dividing both sides by n. And once you do that, once you divide both sides by n, then you've got yourself a fractional distribution function, which is what we're kind of used to. There's a lot of constants out here in front of the function, and that's because once you divide by n, you get nv over n, then you've already got a normalized distribution function. So this has already been normalized. So everything like that is taken care of. Okay? So if you look at this, you can figure out from the distribution functions what these various speeds are. Okay, so here we have our root mean square speed, and from first principles you can derive this expression of root 3 kT over m. So what this is telling us is that for a gas with mass m and temperature T, we can predict what the speeds are. Okay, so this gives us our root mean square speed. The average speed is somewhat lower than the root mean square speed, and that's the square root of 8 kT over pi m. And then the most probable speed is the peak of that curve, and that's root 2 kT over m. Okay, so that's how you get these various values. Now, as you increase the speed, as you increase the temperature of your gas, your average speed increases as well. As the gas gets hotter, the molecules speed up. This makes sense intuitively. And then what happens is the curve starts to look a little less asymmetric and a little bit more Gaussian as you go to higher speeds. Of course, the symmetry gets better because as you skew the peak of the curve to the right, you're moving it closer to infinity, and the curve goes to 0 at infinity. So it makes sense that it starts to look more symmetric as you push that temperature higher. Okay, so that's one distribution function from classical physics, but there's several that I wanted to talk about today. So let's move on to the next one. This is the distribution function for black body radiation. All right. So first of all, let's remind ourselves what black body radiation really is. If you have an old school light bulb, for example, and you start to pass a current through the filament, the light is emitted from the filament. That's due to heat. The light is due to the heat of the filament being heated up by the current, okay? And this is black body radiation. An object at any temperature, in fact, not just really high temperatures, but any temperature is known to emit radiation. If it's a hot object, then it might emit in the visible or the UV. And if it's a cold object, it might emit down in the infrared object. So for example, if you wear night vision goggles, then you can see people even in the dark because we're at 98.6 degrees Fahrenheit and we're emitting black body radiation because of our temperature in the infrared range. Okay, so the wavelength of the light that is emitted by the body is proportional to the temperature of the body. Okay? So at room temperature, as I said, the wavelengths of the thermal radiation are mainly in the infrared, but as you increase the surface temperature, the wavelength is going to change. The wavelengths get shorter as the temperature gets higher. So eventually you'll get into the red glow, eventually white, and then for really hot objects, the UV and the X-ray. So the basic problem was in understanding why the distribution function looked the way they did, because when they tried to use classical physics to describe, it didn't adequately describe the distribution function that they saw from the data. So it turns out that to jump ahead to the solution to this problem, it turns out that photons or particles of light are actually quantum particles, okay? And they obey a quantum distribution function, not a classical distribution function like the one that we saw with the ideal gas law. So what this guy named Max Planck, he studied the distribution function, and he did a fit to the distribution function, and it worked very well to describe, and out of that fell Planck's constant. So here are the distribution functions for various temperatures, okay? So you can see this is plotted versus wavelength here. So since it's plotted versus wavelength, the wavelength gets longer as the temperature gets lower here that you can see, and so it gets shifted to the right. So what starts out, if you're in the visible range at 6,000 Kelvin, which is really super hot, when you get down to 3,000 Kelvin, you've moved over into the infrared. And then, of course, cooler objects also emit in the infrared range. So Planck fitted this curve, and he generated this theoretical expression. And this is what he came up with. He showed that the intensity of the radiation here is a function of the wavelength and the temperature. So here I symbolizes the intensity, lambda the wavelength, and T the temperature in Kelvin. And then he came up with this constant. It was a fit constant, fit to the data, that eventually became named after him, Planck's constant, 6.626 times 10 to the minus 34 joules seconds. So it's a very small number. That's multiplied by the speed of light squared. 3 times 10 to the 8th meters per second is the speed of light. And then you divide by the wavelength to the 5th power, and then E hc over lambda kt. K here is Boltzmann's constant again, 1.38 times 10 to the minus 23 joules per Kelvin, and then minus 1. So this is the distribution function that describes the intensity of the radiation from a black body. And yet again, this is what it looks like. It came from a fit to the data. And then the theoretical description of this curve, the real revolution here, was that it couldn't be described by classical physics, and it was one of the first signals or signposts that the classical physics that we knew about wasn't all there was to the universe, that there had to be something more. And this was one of the things that gave birth to modern physics. Now, I do want to emphasize that this is an intensity function, not a probability distribution function, okay? You can, with a few relatively simple steps, change it from an intensity distribution function to a probability distribution function. To give you an idea of how you might do that, we'll define intensity. Intensity is defined as a power divided by a unit area, okay? So for example, from light, let's say that you have a 60-watt light bulb. 60 watts would be the power of the bulb, and then you're standing 1 meter away. So what that means is that all the light coming from that bulb would be distributed over a sphere with surface area 4 pi times 1 meter squared, 4 pi r squared. All that intensity would be divided over the area of that whole sphere. So if you saw for what the intensity of the light 1 meter away from a 60-watt bulb would be, you get 60 divided by 4 pi, which would give you 4.8 watts per meter squared, and that would be your intensity, okay? Now, a power is an energy per unit time, and of course we have expressions relating the wavelength of a photon to the energy of the photon. So you could easily change this intensity into a number of photons, right, per unit area per second, okay? And in that way, it becomes sort of a number distribution function, which is very easy to convert into a probability distribution function. So that's kind of the way that you would go about it. So you'd have some detector, it would have a known area, you would measure the power output from your photodetector, and then you would be able to convert that over into a distribution. All right, so that's another example of distribution functions used in physics. The third and final one that I want to cover today is radioactivity. Okay, so let's say that you have a radioactive sample, all right, like uranium or something like that, plutonium. What happens then is that the atoms that are in the sample are naturally radioactive, and they're going to decay. When they decay, they're going to emit a particle like an electron, a positron, or an alpha particle, or they're going to emit some radiation like a gamma ray or an X-ray, okay? So they're emitting radiation. And what happens is you have the atom, the excited in an excited state that then decays, okay? And then what you do is you use a counter, like a Geiger counter or something like that, to measure the number of counts that are occurring. Geiger counters just measure a count of radioactivity as a blip, so it just counts it up, okay? Now, what happens is if you have a radioactive sample then let's say that you have some uranium and then it decays by emitting an alpha particle, okay? Well, if it emits an alpha particle, that's basically 2 protons and 2 neutrons, so then it's not uranium anymore, it becomes something else, okay? So, and that something may not be radioactive itself. So then that decay has happened and you've lost that radioactive atom. So what happens is you're losing atoms over time. So the expression is that the number of atoms that decay per unit time, dN dt, is negative lambda times n, where n is the original number of atoms in your sample, okay? Lambda is your decay constant. It determines the rate at which the material will decay, kind of how fast it occurs, okay? And then you have a minus sign here because you're losing atoms. Now, since n is proportional to its derivative, you get an exponential function for your decay. So exponential decays are exponentially decaying curves, okay? So the number of atoms per unit time will decay as an exponential function. Okay, so that looks like this. Here's your decay curve. Let's say that you start off, let's say that you start off with a certain number of uranium molecules or atoms N naught, and then over time that exponentially decays down. Okay, so that's what that looks like. Now, the half-life is sometimes quoted for radioactive materials, and the half-life is defined as the time interval during which half of a given number of your original sample will decay. Okay, so here, for example, it's shown here n to n naught over 2. That's how many remaining nuclei that you have that are radioactive. And there, the time that it takes to go from n naught to n naught over 2 is your half-life. And your half-life is related to your decay constant. The half-life is equal to the natural log of 2 divided by lambda. Okay, and that's pretty easy to see if you just put n over n naught equal to a half and then take the natural log of both sides. All right, it's easy to see. All right, now, we don't really easily measure the number of nuclei in a sample. It's not easy to measure the number of nuclei in a sample, but it is easy to have a Geiger counter there and measure the number of counts, the number of the amount of radiation coming off the sample. That's pretty easy to measure. So instead of n naught, we use the decay rate or activity of the sample, which is usually symbolized with a capital R, okay? And that is the number of decays per second, okay? So that would be equal to the absolute value of dN dt, right? The number of atoms that decay per second would give you the number of counts per second if you take your absolute value. And then that's going to equal to, if you take your simple derivative, lambda n. So you can see that when you take the derivative, you get another exponential function, okay? So your activity is equal to R naught e to the minus lambda t. It's another exponentially decaying curve. So what this says is that over time, let's say that you have a really hot, really radioactive sample. If you wait long enough, right, then it won't be quite so radioactive. The number of decays will drop over time following an exponential curve. The SI units of radioactivity are curies or becquerels, named after people that were pioneers in the field of radioactivity. The SI unit of activity is the becquerel, which is 1 decay per second. But a lot of samples are so very radioactive that that's just not a decent enough number, and so the curie is there for the really, really radioactive stuff. 1 curie is 3.7 times 10 to the 10th becquerels. Okay, well, how do you take these measurements? So we have some radioactive samples and some Geiger counters in the department, so this year I actually went ahead and took some samples. So what you do is you use basically a Geiger counter, like that just measures the number of counts per second, and your Geiger counter will count the number of decays that you observe in a given short period of time. So it'll just say, okay, waiting, and then it'll register the number of counts, and then after the amount of time that you've defined has lapsed, say 5 seconds, it'll stop counting, okay? And then what you do is you take these samples a certain number of time apart. So the amount of time that you use to record the counts might be a short time, like 5 seconds, but then you might take each count, each data point, say 10 or 15 or 20 seconds apart, okay? So that's what I did here. I counted the radiation for a cobalt-60 source that we had, and I let it take counts for 5 seconds each, separating the data points by 10 seconds each, okay? And when you do that, I got a plot that looks like this, okay? I plotted the number of decays observed versus time. So here you see this thing that looks like noise, all right? It looks crazy. It doesn't look like a decaying exponential. Well, it doesn't look like anything. And the time that I allowed it to go was a few hours, okay? So it went for a few hours. But it looks like noise because I didn't let it go long enough. The half-life of cobalt-60 is 5.3 years. So over a few hours, you're not going to really notice too much of a drop in your exponential. So it just looks like a flat decay. So you might be thinking to yourself, why the heck is she showing me this data? It doesn't look like anything. Well, I'll tell you why. Because that's only one of the distribution functions. That exponentially decaying distribution function is only one of the distribution functions that radioactivity obeys. If instead of the number of decays versus time, you plot the fraction or number of decays versus the number of times those decays are observed, then you see a distribution function. So that's what I've done here. On the horizontal axis, I have a histogram here, basically, and on the horizontal axis, I've got bin widths of about, 3 or 4 counts for each bin. Okay, so this one goes, say, from 60 to 63, for example, all right? Something like that, 60 to 64. And then it shows that I measured 60 to 64 counts about 140 times out of all those data points that I took. Okay, so this is the number of times that I observed that particular number of counts, and then I specified a certain bin width. I think it was 4. Okay, now the data doesn't look so noisy and random. It actually looks like it's obeying a distribution function here. I have a perfectly decent looking histogram. Well, it turns out that radioactivity actually follows the Poisson distribution that we learned about in 2210, okay? So remember, the Poisson distribution is this e to the minus mu to the v over v factorial. And here, mu is the average number of counts for a time interval, and v is the actual number counted in a particular time interval, okay? And so here, I fit my data with a Poisson distribution function, and you can see that it's a very nice fit. And for this fit, it shows that the average number of counts, so this would be our value mu, would be 67 counts for each 5-second interval. And then each bin in this histogram is showing you what it would be like, how likely it is to have V counts given an average of 67. Okay, so that's what this fit shows you, and that's the Poisson distribution function. And in fact, the Poisson distribution function describes a whole lot of different counting type experiments, right? We talked about the number of eggs that a farmer finds during a certain time each day, things like that, okay? So it's a counting experiment distribution function, like radioactivity, where each event is independent of the one before it. Okay, and radioactivity follows that. So there's 3 examples of distribution functions from physics to show you and illustrate that this stuff really isn't all that worthless, that it actually has a purpose, and everything that you're learning in here really does pertain and go back to physics. Okay, so hope you enjoyed it, and I'll see you in class.